Imagine for a moment that the greatest scientific conquest of our time is not happening in the stars. It is not happening on distant planets or in the silent orbit of a shiny new spacecraft. It is unfolding inside your body. It is hidden in the tiny mechanisms that decide how fast we age. Now imagine something even more impossible. You wake up and your body behaves as if it still has 20 years of youth stored inside it. Not as a trick, not as a fantasy, as a simple biological fact. Your joints follow your movements, your energy stays with you. Your reflection accepts the rules without arguing. For centuries, this idea belonged to tales whispered across civilizations. People spoke of hidden springs and sacred waters. They trusted potions, rituals, and promises carved into stone. Today the scenery has changed. The quest has moved into cold laboratories where scientists stare at cells instead of stars. Yet the dream remains exactly the same. Understanding how a few rare humans seem to slow down time while the rest of us feel it pressing harder every year. Because aging is not the universal law we believed it was. It does not strike everyone with the same rhythm. Some decline quickly, some decline slowly, and a small minority appears to drift through life as if time does not fully apply to them. And the question is no longer whether this mystery can be solved. The real question is when it begins for us, and how far this revolution is willing to go. In New York, there are centenarians who stand upright, laugh loudly, and stay healthy almost until the final days of their lives. They do not spend years fading. They stay strong until something finally switches off. Scientists call this the compression of morbidity. The rest of us see a disturbing hint that aging might not be as rigid as we once thought. What if these people are not outliers? What if they are signposts? What if their biology reveals the possibility of a mechanism we can observe, understand, and perhaps one day adjust? What you are about to see could transform the way we think about life itself. You will hear how some cells refuse to die and turn the body into a zone of constant alert. You will see how others begin to act young again when their environment changes. You will discover why scientists study blood that seems to push the clock backward. You will meet billionaires who invest fortunes to outrun the end. You will see researchers who attempt to reset a living organism the way you would restart a slow machine. And you will meet people who volunteered to turn their own bodies into test grounds in the hope of pushing the limits of their age. This is not a simple scientific advancement. It feels more like the beginning of a shift. Before we go any further, do yourself a favor and subscribe. If you don't, I will be forced to run a highly questionable anti-aging experiment on you. And while you're safe for now, tell us which mysteries of science you want us to explore next. Your ideas steer this strange adventure. To understand how a few rare humans already escape the logic of time, we must begin with the hidden clock pulsing inside every cell. It sets the rhythm, and for the first time, science is starting to hear it. Somewhere in New York, there is a woman who seems to have missed an important appointment with time. Her name is Lynn Charnay. She is 96 years old and still performs in cabarets as if her body never received the memo that life was supposed to slow down after 70. The lights flare, the music begins, and she walks on stage with the confidence of someone who refuses to negotiate with gravity. People watching her try to understand. They look for signs of frailty. They expect a tremble, a stumble, a moment of hesitation. Instead, they find a woman who jokes with the musicians, throws glances at the audience, and moves with a rhythm that should belong to someone half her age. It is not bravado. It is biology behaving strangely well. When scientists measure her internal state, something even stranger appears. Her biological age is decades younger than her passport suggests. Inside her cells, the molecular scars of time are fewer. The cellular debris that usually accumulates with age is limited. Her body is running on a different timeline. It is as if time were politely walking behind her instead of rushing past. This brings us to the man who has become the chronicler of these anomalies. Near Barzilai, soft-spoken, calm, and equipped with the patience of someone who studies lives that last longer than average. For more than 20 years, he has followed hundreds of centenarians. He has visited their homes. He has examined their blood. He has talked to their families and heard stories of grandparents who gardened at 90, danced at 95, and passed away at 99 after a single bad week. Barzilai discovered a pattern that feels almost unfair. These people do not spend the last decade of their lives fighting illness. They spend most of their lives healthy and then decline in a rapid, almost abrupt final chapter. Doctors call it a compression of morbidity. Nature calls it an exception. The rest of us call it the most desirable bug in human biology. Take a typical lifespan. The last years are often filled with chronic problems, slow deterioration, and long medical lists. For Barzilai's centenarians, those final years shrink dramatically. Sometimes all the decline fits into a season, sometimes into a month, rarely more than a few. Imagine going through life without carrying the heavy weight of a slow unravelling. That is what these people do. What fascinates Barzilai is not just that they live long. Many people do. What fascinates him is that they stay functional. Their muscles remain strong. Their memory holds steady. Their immune systems stay vigilant. Their inflammation levels stay low. They behave like time has been set to a slower speed. Not paused, not reversed, simply slowed. And once you have seen dozens of these cases, you cannot pretend it is magic. The similarities are too clear. Their genes protect them from metabolic chaos. Their cells accumulate fewer errors. Their bodies seem to tune out certain biochemical signals that accelerate decay. They do not hack aging. They ignore part of it. This is the moment where the story becomes uncomfortable for the rest of us. If some humans can age at half speed, what does that say about the rest of us? Are we unlucky? Are we missing something? Are we running with outdated cellular software while they secretly run the premium version? Scientists do not have a full answer, but they do know this. These people offer clues. Their blood, their genes, their metabolic rhythms, their immune responses. Each detail is a piece of a much larger puzzle. A puzzle that could reveal why time flows faster in some bodies and slower in others. And here is the turning point of this entire investigation. If their timeline can slow down, then our own timeline might be adjustable too. Which leads us to the next step. A step away from the bright cabarets of New York and into the microscopic machinery ticking inside every living cell. Because before you can imagine modifying the pace of your life, you must understand the instrument that measures it. To slow an internal clock, you must first learn to read it. To understand why some people age slowly while others sprint toward decline, you have to meet someone who has spent her life staring at the secret timeline hidden inside the body. Her name is Morgan Levine. She walks into a lab the way a detective walks into a crime scene, calm, sharp, and slightly amused by the chaos of biology. She studies aging not through birthdays, but through chemistry. She looks at DNA and asks a strange question. What if the real age of a body is not written in the years, but in the marks left on its genetic material? Marks so small that microscopes miss them. Marks left by food, by stress, by pollution, by sleep, by every decision we make across a life. This is the world of epigenetics. Imagine your DNA as a master recipe book passed down through generations. The instructions never change. What changes is how well the text can be read. In youth, every line is sharp and clear. But with time, the pages wrinkle. Ink smudges. Margins fill with confusing scribbles. Some sentences fade, others darken. The recipe becomes difficult to follow. Cells try their best, but when the text grows chaotic, mistakes appear. Too much of one protein, too little of another. A molecular version of adding sugar when the recipe asked for salt. Small errors repeated millions of times become aging. Levine realized these chemical marks were not random. They followed patterns. They formed a map. And if you fed thousands of these patterns into powerful algorithms, a hidden clock appeared. A biological clock. One that could tell how fast a body had really traveled through time. When she first tested herself, she felt a familiar thrill mixed with a hint of terror. Her birth certificate said 36. Her biological readout said 31. 5 years younger on the inside than the outside. Not immortality, not magic, just a quieter rhythm at the molecular level. The discovery is unsettling. It means time moves differently in each of us. It means your true age is not the candles on your cake, but a silent chemical story unfolding in your cells. And it means something even more radical. If the clock is chemical, then the clock can be changed. Not easily, not safely, not without enormous knowledge, but in theory, it is not fixed, it is adjustable. Aging is not only a march forward, it is a mechanism, and all mechanisms obey rules. To follow the trail even deeper, we need to find the next piece of the system, the one that counts cell divisions like a cosmic odometer, the one that shortens with every replication. Because every mechanism has a countdown, and ours is waiting at the end of each chromosome. If the biological clock tells us how fast we age, telomeres tell us how far we can go. They sit quietly at the ends of our chromosomes, small protective caps that decide how long a cell can keep dividing before giving up. Maria Blasco studies them as if they were sacred artifacts. She loves to explain them with a simple image. A chromosome is a shoelace, and the telomere is the little plastic tip that keeps the lace from unraveling. Every time a cell divides, the tip shortens. It never grows back on its own. The countdown begins at birth and continues silently through childhood, through adolescence, through every decade when we pretend time is not chasing us. As the caps shrink, the DNA beneath becomes exposed. Errors slip in, proteins misbehave. Eventually, the cell reaches a point where it can no longer divide. Its last act is to declare itself old. This is one of the fundamental truths of aging. A shrinking piece of biological plastic decides how long our tissues stay young. Blasco wondered what would happen if you stopped this countdown, or even reversed it. So she worked with mice and gave them an extra ingredient. Not a drug, not a vitamin, a gene. The gene that produces telomerase. An enzyme able to rebuild those protective caps. It was as if she handed the cells a fresh box of plastic tips. The results were astonishing. Mice lived longer. Their tissues aged slower. Their risk of cancer dropped instead of rising. It was the scientific version of watching a worn machine suddenly move with the calm elegance of something far younger. And this is where the story takes a turn from scientific to nearly cinematic. A woman named Liz Parrish reads these studies and does not react like a typical observer. She does not wait for clinical trials. She does not wait for approval. She does not wait for anyone. She decides to try it on herself. She travels to Colombia without telling her family. She enters a small clinic. She lies down. She receives more than 100 injections carrying the gene for telomerase. She walks out claiming she has become the first human to attempt a direct molecular rewind. She becomes patient zero in the underground history of radical longevity. According to her lab results, her telomeres grew longer by a measurable percentage. She says she has gained 20 years of biological youth. Scientists argue, regulators panic, reporters shake their heads, but she continues. She even repeats the experiment 5 years later with new genes designed to boost regeneration. Behind the controversy, one idea grows louder. If telomeres can be rebuilt, then aging is not a one-way road. It is a loss of information, and information can be restored. This is the belief of David Sinclair, the scientist who frames aging not as decay, but as a corrupted file system. In his view, the body still holds the original instructions for youth. The problem is that time scratches the disk. The solution is to repair the scratches. This sets the stage for one of the strangest biological truths yet. Some cells do not die when their telomeres vanish. They stay alive. They stay dysfunctional. They refuse to leave. And they become something far more unsettling than simple old cells. Something we will soon meet. Cells that no longer divide, but refuse to die. Cells that accumulate with age. Cells that behave almost like the undead. Because the next discovery in longevity research is not elegant at all. It is disturbing. Some aging cells become zombies. Imagine a cell that grows old but refuses to die. A cell that stops dividing yet somehow stays alive. A cell that does not contribute anything useful and still insists on occupying space. Judith Campisi has spent decades studying these biological freeloaders, and the more she looks at them, the stranger they become. They are called senescent cells. Under a microscope, they look like swollen giants, flattened and bloated. They are the elderly residents of our tissues, too tired to work yet too stubborn to leave. The problem is not that they exist. The problem is what they do once they settle in. Instead of retiring peacefully, they begin to secrete a chemical cocktail that spreads through the nearby tissues. Inflammation, cytokines, signals of stress, little molecular cries that pull the body into a state of constant alert. It is like living in a city where every emergency siren rings at the same time, every day, without a break. Police everywhere, fire alarms everywhere, no silence, no rest, no chance for anything to repair. This constant state of alarm accelerates almost everything we consider part of aging. It damages joints, it weakens muscles, it clouds memory, it accelerates cancer, it pushes the immune system to exhaustion. Senescent cells do not just age on their own, they force everything around them to age faster. Here is where the story becomes even more intriguing. Those super agers we met earlier, the ones who live past 100 while behaving like they are 60, have fewer of these zombie cells. Their bodies clean them out more efficiently. Their tissues stay calmer. Their organs stay quieter. time moves through them more gently. And now the idea becomes impossible to ignore. If senescent cells speed up aging, what would happen if we removed them? What would happen if we cleaned the city? What would happen if we quieted the alarms? Some scientists believe the answer is simple: slower aging, healthier aging, possibly even partial reversal of aging. Others say the idea is dangerous, too bold, too unknown. But one thing is certain: when you identify an enemy, you make a choice. You either ignore it or you prepare for a fight. And that is exactly what is happening right now. Researchers are preparing new tools. Pharmaceutical companies are racing to find weapons. And some of the richest individuals on the planet have decided that this battle deserves their money. Because when you declare war on zombie cells, you need more than courage. You need an army. And the next part of this story begins with the scientists who decided to build one. If zombie cells are the enemy, James Kirkland is one of the first scientists who tried to fight them with actual weapons. He worked with old mice that moved slowly and breathed heavily and seemed ready to retire from existence. Then he gave them molecules designed to push senescent cells toward death. What happened next looked almost like a special effect. The mice moved faster, their fur looked cleaner, their muscles held more strength. They explored their environment again. It was not immortality, far from it, but it was enough to make the scientific community freeze for a moment and ask the same question: what have we just seen? And that is when Silicon Valley smelled the future. Jeff Bezos, Peter Thiel, and a small constellation of wealthy futurists poured money into a new company called Unity Biotechnology. They imagined a world where the first anti-aging drug would not come from mythology, but from a biotech startup living next to a coffee bar and a ping-pong table. The dream did not last long. Unity launched a clinical trial on patients suffering from osteoarthritis. The early data looked promising. The final data did not. The trial failed. The company lost most of its value in a single day. The dream of an immediate cure dissolved. Nature reminded everyone that she does not surrender easily. Still, the researchers refused to stop. They shifted to a new target: the retina, a place where senescent cells quietly damage vision with age. Early signals began to show improvement. Not a miracle, not a revolution, a small light in a long tunnel, but enough to keep the war alive. And while venture capitalists chased futuristic drugs, one man returned with a much older molecule. Near Barzilai, the calm scientist from earlier who studies centenarians. He looked at data from millions of diabetic patients and found something strange. Those treated with a generic drug called Metformin seemed to live longer than those who did not. They also developed fewer cancers, fewer cardiovascular problems, less cognitive decline, as if this quiet, inexpensive pill had been hiding in plain sight for 40 years. Barzilai wants to test Metformin on healthy older adults in a massive clinical trial to see whether it truly slows aging. He calls it TAME, a polite name for a wild idea. Treat aging itself as a medical target rather than a background tragedy. But while scientists debate molecules and clinical trials, a very different character storms into the story. His name is Brian Johnson. If the previous researchers built laboratories, Brian tries to become one. He measures more than 200 biomarkers every day. He eats meals calibrated to the gram. He tracks every heartbeat and every fluctuation in his microbiome. He takes supplements with military precision. He calls the project Blueprint. Others call it a very expensive midlife crisis, but no one doubts his determination. Then came the moment that turned him into a headline: the transfusion. First he tried plasma from young donors. Then he reversed the flow and transferred plasma from his father into himself, and from himself into his teenage son. A dramatic experiment that sparked outrage, fascination, mockery, and scientific debate. It was one of the most controversial acts in the entire longevity world. Yet behind the spectacle lies a simple truth. Brian Johnson is not trying to sell an idea. He is trying to test one, on himself. He represents a new kind of human, the living prototype, the volunteer for experiments that have not yet reached approval, the person willing to treat his body as an open laboratory. It is chaotic. It is bold. It is uncomfortable. But it marks a shift. Longevity is no longer only a scientific question. It has become a cultural one, a personal one, an existential one. All of this raises a final question that pushes us into the next phase. Some scientists are not satisfied with improving the body. They want something far more radical. They want to reset it. There is a moment in the history of longevity research when the story suddenly feels less like science and more like a lost page from a Gothic novel. It begins with an experiment that should not exist, yet does. In a quiet laboratory at Stanford, Tom Rando connects an old mouse and a young mouse by their circulatory systems. The two animals share blood. They share molecules. They share time. What happens next shakes the field. The old mouse begins to move with more confidence. Its muscles respond better. Its tissues heal faster. Even its organs show signs of renewed vitality. The young mouse, meanwhile, slows down. Its tissues behave as if they have aged. Its internal chemistry darkens. It is as if the age of each animal has spilled into the other through the bloodstream. The idea is almost frightening. Age is not only inside the cells. Age floats in the blood. Researchers call the method Parabiosis. Everyone else calls it a Frankenstein experiment. Yet the results, no matter how disturbing, force the scientific community to look twice. Of course, attaching two animals together forever is neither practical nor ethical. So another team tries a gentler approach. Instead of sharing entire circulatory systems, they isolate the youngest part. Plasma, the golden liquid that carries proteins and signals throughout the body. Tony Whisk-Corey begins injecting old mice with plasma collected from young mice. No surgical connection, no shared organs. Just one infusion after another. And something remarkable happens. The old mice perform better in memory tests. They solve mazes they once forgot. Their brains create new neurons, something thought to decline sharply with age. A small river of youth flows through their veins, and the brain seems to remember how to repair itself. This discovery escapes the lab and enters the imagination of entrepreneurs. One startup sees an opportunity. It is called Ambrosia. It offers transfusions of young plasma to wealthy clients who are willing to pay thousands of dollars for the privilege. $8,000 for 2 liters of youth. The idea spreads fast. Then the American health authorities react even faster. Ambrosia is shut down. The party ends before it begins. Behind the spectacle lies a deeper truth. Blood is not magic, but it carries a vast library of signals. More than 1,300 proteins change with age and shift the behavior of cells. Some of these proteins maintain youth. Others accelerate decline. Together they form a molecular fingerprint of time. Scientists begin mapping the fingerprint, They create charts. They identify clusters. They find molecules that predict resilience and others that predict decay. For the first time, blood becomes not just a fluid, but a biochemical diary of aging. And everything we have seen so far, from Frankenstein experiments to forbidden transfusions, is only the beginning. Because the next breakthrough is not about borrowing youth from another body. It is about unlocking the forgotten instructions of youth already hidden inside our own. There is a moment in every scientific field when the story changes from slow progress to something almost frightening. In the world of aging, that moment begins in a laboratory in the French town of Montpellier, where Jean-Marc Lemaitre keeps hundreds of cells from very old people stored in frozen silence. Some belong to centenarians. Some are already senescent. All of them carry a full lifetime of molecular scars. Lemaitre does something unthinkable. He introduces a set of 6 messenger molecules into these ancient cells. They read the code. They rewrite instructions. And slowly, the cells begin to change. The wrinkles on their DNA fold back into place. Damaged proteins disappear. Energy flows again. Under the microscope, it looks as if time were being pulled backward. The result is surreal. Cells taken from people who lived a century regain the behavior of youthful cells. They divide again. They move again. They respond to signals again. They can even transform into beating heart cells, tiny biological engines contracting rhythmically in a dish. A small heartbeat created from the molecular memory of a human who may no longer be alive. This alone would reshape our understanding of biology. But the field does not stop at dishes and microscopes. Researchers wonder whether the same idea could work inside a living animal. Not a cell, not a tissue fragment. An entire organism. They modify mice to carry a genetic switch. When activated by a simple molecule, the switch triggers a brief wave of reprogramming inside their bodies. The effect is astonishing. Their tissues behave as if someone had polished their molecular machinery. Their organs show signs of rejuvenation. Even their lifespan increases. The idea that once belonged to folklore now walks around in the form of a mouse that ages more slowly because its cells were briefly convinced to become younger. And then comes the scientist we briefly talked about previously, and who turns this field into global news. David Sinclair. Sinclair believes aging is not a slow decay, but a loss of information. He compares the epigenome to a corrupted software file. The instructions for youth are still there, he says, but the operating system has forgotten how to read them. His solution is simple in theory and terrifying in practice. Restore the instructions. Using 3 of the famous Yamanaka factors, Sinclair triggers controlled reprogramming inside the eyes of old mice. These animals have damaged optic nerves. They cannot see. They have aged far past the point of natural repair. After treatment, something extraordinary happens. Their vision returns. It is the first credible demonstration that the age of a living tissue can be reversed. Not paused, not slowed, reversed. As if a piece of the body glanced backward through time and remembered how to function like it once did. This is the scientific peak of our journey. Cells rejuvenated. Tissues restored. Organisms that grow older more slowly. Blind mice that see again. And yet, the climax of the story does not end here. Because while laboratories rewrite the code of life with tools we barely understand, another truth emerges. Some of the most powerful ways to influence aging are not futuristic at all. They are already within reach. They are simple, they are natural, and they do not require injections, gene switches, or billion-dollar laboratories. But that part of the story has its own twist. After a journey filled with gene therapy, glowing mice, billionaire experiments, blood transfusions, and molecular time machines, the story arrives at an unexpected place. It arrives in the quiet rhythm of daily life. It arrives in habits so simple that they almost feel unfair after everything we have seen. The future is spectacular, yes, but the present already carries more power than we think. This is the territory of Valter Longo. He moves between Los Angeles and Italy with the calm assurance of someone who has spent decades listening to the language of human cells. He studies what happens when the body experiences short, controlled periods of scarcity. A biological whisper that wakes up old systems. He created the fasting mimicking diet, a sequence of 5 days where the body believes it is fasting while still receiving nutrients. The effect is not magical, it is mechanical. When the body enters a state that mimics fasting, it begins to clear damaged cells, recycle broken parts, and restart immune pathways that were asleep. Longo tested this in clinical settings and measured something astonishing. 3 cycles spaced over several months reduced biological age by nearly 2.5 years in the average participant. He also observed immune rejuvenation. Elderly volunteers saw new immune cells replacing old dysfunctional ones. Other researchers began to use fasting protocols in models of neurodegeneration. In some cases, early signs of Alzheimer's seem to soften. Not a cure, not a miracle, a spark. And sparks matter. Exercise carries another one. It does more than strengthen the heart. It sends molecular messages throughout the body, awakening mitochondria and triggering the release of small proteins that act like youth signals. These proteins calm inflammation, sharpen cognition, and stabilize metabolic rhythm. Even simple movements have measurable effects. A daily walk lowers biological age markers. A regular swim changes mitochondrial density. A consistent practice of strength training slows the epigenetic clock in ways that echo the benefits of advanced therapies. Sleep often escapes attention, yet it remains one of the most powerful longevity tools ever discovered. During deep sleep, the brain cleans itself. Damaged proteins are washed out. Hormones that repair tissues appear. A single week of poor sleep can age the epigenetic clock faster than months of physical inactivity. A single week of good sleep can reverse part of the damage. Stress follows another path. When stress persists, inflammation rises. Telomeres shorten faster. Senescent cells accumulate. People who meditate regularly or follow structured breathing routines show slower biological aging. Not because meditation is mystical, but because it teaches the body to exit the emergency mode that accelerates decay. Nutrition completes the picture. A diet rich in plants, fibers, and unprocessed foods reduces inflammation. It stabilizes the microbiome. It supports the immune system. Populations following the Mediterranean pattern consistently show better health in old age. Not immortality, just a graceful trajectory. This is the paradox of longevity. The world spends billions trying to modify the deepest machinery of life. Yet some of the most powerful levers are free. They hide in morning routines, in daily meals, in small decisions, in quiet discipline. And while the future promises astonishing breakthroughs, the present reminds us that biology listens closely to the simple choices we make every day. This calls for a final smile, the kind of smile that comes after a long journey filled with futuristic dreams and strange laboratories, because the truth is elegant. In the end, your cells care more about broccoli and walking than about billionaire blood. And now comes the moment where I turn the question to you. If aging becomes adjustable, what will you do with that freedom? If time becomes flexible, how will you choose to live? If science gives you more years, will you fill them with the same habits, or will you become someone new? Tell us in the comments which side of this future excites you, scares you, or inspires you. See you soon for another wild ride into the strange, brilliant, and slightly terrifying future of science.